Oh, I think I'm gonna mess up. We won't hear that anymore. I was just worried because sometimes, depending on what I have plugged in, the audio doesn't always come through. So, all right. If we take a look at this list of terms, there are many that we already are good on. So, for example, Dante, which one are you like, Ms. Garrett, we're good. We already have talked about that. Heck yeah. Taste? Precipitate? Precipitation reaction are like good. So we know what those are. Okay. Before we look any further, could you please find the very last page? So I know, ladies and gentlemen, that yesterday we were presented the solubility table. And then on this page, I asked us to determine per the solubility table if F and J were soluble or insoluble. So could I have us start today by determining if D and E, soluble, insoluble, G, H, and I. So can we take a moment, apply the solubility rules that are communicated with the table? If we are on the very last page of our little packet and we applied the solubility rules, two of these, the rest, we're just warming up with that. It will take 30 more seconds. If you're asked, is it soluble or insoluble, it is absolutely sufficient to write an I or an S. If you're asked that question, we can definitely abbreviate. So let's be crazy and go backwards. Isaac, what about I? Insoluble. Wait, I or S?
I.
Do we agree?
Said that sulfides.
And is iron an exception that would make it soluble? Nope. I apologize. I asked you to repeat, not because you were wrong. I couldn't distinguish. Did you say insoluble or soluble? Do you mind also giving us H? Yes. And not so worried about that. What about Connor? G.
Yes.
Yeah. Ammonium, always soluble. Doesn't matter what it's with. Brooke, how about E? Perfect. Adam, D. Perfect. Any questions? Okay, so if you know it is insoluble, Alex, when you add it to water, what do you know we'll observe? So yesterday, the last two beakers, you added calcium carbonate and magnesium hydroxide. Do you remember what they look like?
Remember, like, did it become like cloudy white?
Yeah. So solutions, are they cloudy? No, they're clear. They can have a color, but they're clear. That's different. Do we understand? Okay. And so insoluble, we know because it's cloudy. Now it doesn't have to be white. It's not clear. All right. So how do we know if a precipitation reaction will happen? How do we know if a reaction? So we know if something is insoluble because we get a cloudy solution or not a cloudy mixture when we try to dissolve it. How do we know if we're going to get a precipitation reaction? Okay, could you please, and I apologize, these are not numbered. So with the cover, page 1, page 2. So what would be page 3? It says on the top, writing net ionic equations. Okay, so Eva, choose for us, 1 or 2. Perfect. All right. Will a precipitate form if we combine solutions? So you will be given wording in the problem that will help to let us know, oh, we are definitely looking for precipitation. Okay, solutions of potassium nitrate and magnesium sulfate. All right, so for number 2, potassium nitrate. I know, Ryan, you'll slam dunk. What is that formula? You got it. You got it. What phase symbols are they?
Solid. Liquid.
Okay, so if it just said potassium nitrate, nothing else, absolutely solid. Ionic compounds, all solid at room temperature and pressure. So very good. So I understand you thought liquid. Well, then it would have to be hundreds and hundreds of degrees Celsius. No. A solution of it, unless otherwise told, it's dissolved in water. So we know as soon as we see solution, we can attach aqueous. We don't have to check solubility rules, anything. Okay, is reacting with magnesium sulfate. Sean, what formula? Excellent. All right. Ellie, what kind of reaction will that be? And when I say kind of reaction, I mean the 5 categories we learned: combustion, single replacement, double replacement, decomposition, composition.
Would it be double replacement?
Absolutely. Absolutely. So potassium and magnesium will switch partners. So we'll get KSO4 plus 1 minus 2. So K2SO4. And then MgNO3 2. Okay. It's asking us if we will get a precipitate, a solid formed from the mixture of 2 or more solutions. So you see, we're setting ourselves up reactant-wise. Go ahead, ma'am. Oh, for heaven's sakes. I was so excited to start to talk about, yeah, thank you very much. God bless you. Thank you. Thank you, Ron. You're very, very much. You're absolutely correct. Okay, so how do we know what phase symbols? Go. Yep, check their solubility in the solubility tables. You will never have to memorize that. Those, I will always provide that same exact sheet when we need it. So Could someone please check for us? Go, sir.
Yes.
Yeah. Potassium compounds, always soluble. We don't have to check the sulfate category. Nitrate, always soluble. So, precipitate? No. Do we have a driving force? So, our driving forces, precipitate? No. Are we producing a gas? No. We identified these. Now, do we understand water is there in the background? So if these have a chance to dissolve, they will. So that's why those aren't in the solid state as well, just because they're ionic. Not a gas. Do we form water? Nope. And I would have to give us more guidance with transferring electrons. So if we don't have our ions changing charge, we know electrons were not transferred. So all right, $2,500 question of the day. Why no reaction? There could be several correct answers.
Like the one list that we got, I don't remember what it's called.
That is okay. We don't have to like know that term. I mean, it's great if we do. Driving force. So it's not satisfying making water, making a gas. So there's no driving force. There's no driving force. Hunter, do you mind? You enjoy running? That is great. That I admire very much. The only part of running that I like is when I'm stopping, if you don't mind me saying. I admire that. Like people that like get up really early and like run 3 miles. I would just rather do other forms of exercise. Okay. So, I don't know, motivation for me to run. I would definitely choose other things where you enjoy. There's motivation for you. So there's nothing motivating. No reaction. So excellent, excellent, excellent. Fruit juice, okay? Oh my goodness, what am I thinking? But what else could we say? Why there's no reaction? Ionic, soluble, it'll dissociate. Yes, sir.
Nothing changed because they're all electrolytes in this state.
Is it, can I just continue? Do you mind? Okay, when you say nothing changes, what do you mean? Could you be a little more detailed?
Like they're all dissociated ions at this point. So like the 2K plus is the same on both sides, like nothing cancels out in the net ion. But while everything cancels out, because it's the same on both sides.
So when you say nothing changes, I mean, sometimes we show physical changes with like an equation, but we're after chemical changes. And so a chemical change produces something new with totally new chemical identity. Well, two potassium ions, not changing. Two nitrates, not changing, not changing, not changing. Sean, were you going to say something?
I was gonna say that aren't they all affected?
Yes. So what you said, those are the best answers to what I was speaking of. Excellent, excellent. There's no spectate or there's no driving force. They're all spectators. Alex, if for your birthday, your parents blessed you with 4 tickets, to your favorite musical artist, who would that be?
Double garden.
All right. I have no idea if that is school appropriate. So I just hope just naming it is okay. All right. So you have the tickets. Let's say it's Saturday night, 8 p.m. You show up. You're the only 4 there. You're there. No concert. These are there. Nothing's going on. You're not creating water. You're not creating a precipitate. So they're just all looking at each other, hanging out. Not that they're looking at each other. There's no driving force. So you're just making a mixture. Okay. So there's no net ionic. Oh, Sean, are you thinking about just being there? Are you thinking about who you would like to see? Okay. A 2 hours of chemical reaction demonstrations. Everyone's dream. I know, so you wanted to say, Ms. Garrett, that would be what I want.
I would broadcast.
Absolutely, absolutely. Okay, questions? All right, so if we go back to our list. Okay, so what we created, what I just wrote out, is what we call the ionic. And the ionic shows species that are existing as ions if they are. Now, can I just show you a reaction just to take a look at it? The decomposition of calcium carbonate solid. With heat, we know we are going to get calcium oxide and carbon dioxide. Driving force still in? When I say driving force, production of water, production of precipitate. It could be transfer of electrons, but I'm not going to present that to us. Remember the other? Making a gas. So that's why this reaction happens. You are creating a gas. Will anything here really be existing as ions? No. So we would call this the full equation. It's not that we don't have an ionic equation. It's just the same. And then the same net ionic. So it's not that we don't have those other versions. They just won't be any different. I believe I was negligent in making sure we understand this. So you don't have to, we're going to come back to this. The page. So we improve upon our understanding as we learn through this course. So talked about like visualizing things. If Anna made a solution of KNO3, that's what she would write on the bottle and then the concentration. So maybe it's 0.50 molar. But what we have to understand is this is not water with a bunch of potassium nitrates. It's water with dissociated ions. That's why this is a better expression, because that's what we really have. If we would satisfy driving force, let's just say, if these were not dissociated in solution, they wouldn't react if we would mix solid with solid. So as chemists, we often will rely on dissociation to actually get a driving force to be satisfied. All right, going back to the list. Once, and you saw this with the packet yesterday, once you cancel spectators, then you have the net ionic. The net ionic is the most important equation. In fact, my second year students, that's all they ever give. Me and the AP Chem exam. It will just say, provide the net ionic equation. They're doing an identification lab this week. They're just giving me the net ionic. I don't care about spectators. They're not being changed. We just care about what is really driving the reaction to happen. Electrolyte, we got that last. That is where we have free moving ions. And so the first solution you made yesterday, urea and water, no free moving ions. If we tried to light the light bulb, nope. But all the others that were soluble would light the light bulb. So the urea in water is a non-electrolyte. The next three that were soluble, electrolytes. Driving force, aqueous. Does anyone need, though, any of those terms addressed? Spectator ion. Dissociation. Right, so ionization. I'm going to go to one of those pages that were blank. All right. How we found out that ionic compounds dissociate was in their ability to light a light bulb. And we just assumed, oh, all covalent molecular, nope, not going to light the light bulb, which happens with the grand majority of them. So we know, oh, no free moving ions. There's some covalent that do light a light bulb. So they must create free moving ions. So it was that experimentation that led us to this concept. All right. Ionic soluble compounds dissociate. Period. End of story. Acids in solvent ionize. So if we would give a definition to ionization, ionization is the creation of ions from or by the reaction. Oh, shucks, sorry. By the reaction of acid plus solvent. All right, so creating ions, but take a look. Reaction. Okay, I'm sure that we remember. How do we recognize, Ali, if something is an acid? Do you remember?
If it's above 7. I don't know, above 7 pH?
And pH. Actually, acids are below 7.
Sorry.
Totally fine. Totally fine. We're not to that learning yet. So if we tested something with hydronium paper or pH paper, indicator paper, litmus paper, that could help us narrow it down. Yeah, go ahead, Alex.
I want to start with hydrogen.
So if we have the formula, we have the hydrogen ion first. Okay. Any acids, Alex? Very good. Very good. Very good. Any acids that you remember? You can just give me the formula.
Hydrochloric acid.
Go ahead.
Uh,
Oh, are you going to keep going?
no, I don't know anymore really.
You're being humble. I think you gave us the best one because I think that's the most well known, but I could be incorrected. Okay. We know acids have pH below 7. Is there anything else that you know about acids? Are there any other properties that you associate from learning about acids outside of class or in other classes? Go ahead, sir.
This is just like a generalization, but aren't they mostly liquid?
Most. The ones that we will deal with. So, even though we call this hydrochloric acid, it does not have the properties we associate with it being an acid until it ionizes. So it's going to be interacting with water and producing liquid. So that's why, yeah, we can make that association. But there are definitely solid acids. So we're going to find them in the solid or liquid state. Yeah. But the ones that we generally work with are in aqueous solution. So we can go with that.
What about like citric acid? On sour candy.
Yeah. So citric acid is actually solid, but it doesn't show the properties of acids until it ionizes with water. So we call it an acid because the only time we're really going to interact with it is if we put it with water or put it with a base. And then it shows us this thing. Yes, sir. Ah. How about reacting with things? So could you repeat again? The more concentrated the what? So how do we get, so the greater the concentration of HCl or, yeah. How do acids taste? Yeah, sour. So I bet there's things you've learned before. Okay, the deal is to have a pH below 7, to be sour, to be so reactive with metals, which acids normally are, something has to be created. So even though we call this hydrochloric acid, it's not until it does this with water. Okay. So good, Isaac. Acids are hydrogen ion donors. That's how we define an acid. Hydrogen ion donors. Now, there can be some exceptions, but that is the overwhelming majority. Okay. What on earth does that mean? Okay, Ethan. I am saying acids donate hydrogen. They're going to give it away. What will be left if HCl loses the H plus? Cl?
No. Good.
Well, that's still chlorine. That would be so bad because chlorine is deadly for us to inhale at very low concentrations. That'd be really bad. Go.
Cl minus 1.
Ah, chloride. And there's water there. Now, the phase symbol we put on water is liquid because we wouldn't have water dissolved in water. That's kind of weird. Yeah. And we acknowledge that the HCl is dissolved in water. But while in water, it does this reaction. Okay, so it gives away the hydrogen ion. It then creates this chloride. But what else is made? So where does the hydrogen ion go? The HCl gives. What takes it?
I was gonna say, does it just become a gas?
No, that's a good guess. No, so it's not going to just, become H2 and bubble out of solution. Do you just have oxygen as a reactant? What's the other reactant? Water. Acids give away the hydrogen ion only if what they're reacting with can accept it. That's the only thing that happens between these two reactants. So if we would add H plus to water, what's our formula? Easy peasy. Just add H plus. How many hydrogens? Yeah, 3. How many oxygens? Just 1. We added H plus to a neutral compound, what's the charge? Yep. All right. So ladies and gentlemen, like Isaac, when you said like H plus, when we say acids taste sour, when we say they're very reactive with metals, it's this. It is that has all the characteristics we ascribe to acids. This is given a special name. It's called the hydronium ion. It's this that we're measuring to deliver a pH value. Okay, another acid is hydrocyanic. Okay, Rania, I am telling you it is an acid, plus we can recognize from the formula, it begins with the hydrogen ion, which in our kind of chemistry, that's how we write acids. But it doesn't really become an acid until it can react with water. Okay, I'm telling you this is an acid. Acids donate the hydrogen ion to what they're reacting with. Can you give me one of our products? Yeah. The cyanide ion. And then hydronium. Okay, so that's what acids do. Acids give away the hydrogen ion. If they're interacting with water, it makes hydronium. And that is what gives an acid all its characteristics. Okay, buckle your seatbelts, because HCl with water gets a one direction arrow. But this acid with water gets a back and forth. Okay, what's the difference? You know. So the full arrow, what does that mean? I start with this and I end with this. Now, of course, I could have a limiting reactant, but I'm going to make as much product as we possibly can. Go, ma'am. In fact, when they're equal arrows going to form products and then products reforming reactant, what do we call that special situation?
Equilibrium.
Equilibrium. Remember, equilibrium does not mean equal amount. It doesn't mean we have the same amount of product and reactant, but it's the same rate of change. So if we have 3 reactant becoming product, well, then we have 3 product, even though we can't have an odd number. But anyway, 3 becoming. Okay. HCl is what we call a strong acid. But now we're just going to put it. Okay. HCl is what we call a strong acid. HCN is an example of a weak acid. And with acids, it's either extreme. There's no like, well, it's kind of acidic or it's medium. You're either strong or you're weak. No in between. Okay. Strong acids ionize 100%. Weak acids ionize 1 to 3%. What does that mean? I know Connor has a great thought. But I also know, Ava, you are a great thinker. Alex, great thinker. I don't want us to say, oh, we know that Chase will answer, or Connor will answer, or Sean will answer. Brooke, you are a very, very good thinker. So I have faith that all of us. Take it away, sir.
I could be off base with this, but does that mean that equilibrium is reached with only 1 to 3% of the amount of the weak acid put in being ionized?
So this is what makes something an acid. If we place 100 HCN molecules into water, then, Dante, if we start with 100 of these, only ionizes 1 to 3%. How many hydronium in reference to the 100 will we have? Yeah, so choose 1, 2, or 3. Sure. Hardly any. Hardly any. But Sean, if we have 100 HCl, how many hydronium? Yeah. Can we just write down the strong acids? There's only 6. HCl is one of them. HBr, hydrobromic, hydroiodic. Nitric acid, sulfuric acid, and then perchloric acid. There are thousands and thousands of acids. Only 6 of them are strong. So if you're given another acid and it's not one of these, you know it's weak. Okay, so we need to work with these with ionic and anionic, but we haven't yet. So, ladies and gentlemen, applying solubility rules and the ionic and net ionic stuff, could I ask us, it is page 7. Page 7. So the example that we did together, will a precipitate form? So I'm telling you, there are solutions. So exactly the thinking we did, can you do for 1, 2, 3, and 4? If there is not a precipitate or a driving force, all you have to get is the overall equation. That's it. Okay? Have a wonderful weekend.